Yeah. Hello, everybody. Welcome to today's crime seminar. Today we have two speakers. Our first speaker is Professor George Bollas. He will be giving a talk on physics-informed machine learning through symbolic regression. Dr. George Bollas holds the Pratt & Whitney Endowed Chair Professor in Advanced Systems Engineering at UConn's Chemical and Biomolecular Engineering Department, and he directs the Pratt & Whitney Institute for Advanced Systems Engineering at UConn. He is a former postdoctoral fellow at MIT. He earned his bachelor's and PhD in chemical engineering from Aristotle University of Thessaloniki in Greece. His research integrates energy technology, process, and model-based systems engineering, focusing on cyber-physical systems design, optimization, and maintenance. He has received numerous awards, including the NSF Career Award, among others. Prof. Bollas, now the stage is yours. With that, you can start your presentation.
Thank you, Naza and Min. And that's one of the few times that the Aristotle University of Thessaloniki is pronounced correctly. So I guess working for another Greek professor gives you excellence or the capability to pronounce Greek stuff right. I'm very glad that I was invited to give this webinar. And I started with including some slides about the Institute and what we do in the Institute. Eventually ended up with way too many slides, so I'll skip that and I'll just jump into the focus of the presentation. And we started by actually working on physics-informed machine learning. The idea started about 10 years ago. Someone, a senior professor, very successful, asked me, what's your goal in research? What's your goal in life? That's a deep question. And I said I would like to be able to predict nature and from data. And that was before the explosion of machine learning and everything that goes on right now, and AI and so on. But along these lines, we got funding to explore manufacturing, system maintenance, and things like that, that in many cases integrate data with physics and start exploring ways to actually develop what's called glass box models and transparent models. So I have some motivation slides here. Oops. I don't know, the video now is not playing as well, but anyway, that shows manufacturing and precision machining specifically. We've had a few major projects on that. Why is it not playing? Let's try again.
Yeah, we checked it before, yeah.
Okay, so the left-hand side shows really bad manufacturing application where you see smoke and fire and sparkles and things like that. And the left-hand side shows a more smooth manufacturing. And the goal in many of our projects is to actually use models, what's called the digital twin, that integrate physics-based machining models and data-driven models. And in manufacturing, you need data-driven models because many of the physics are ill understood, and a lot of the data that are collected could be vibration or audio or other types of data that do not integrate well with physics-based models. So we started thinking of how we would integrate physics with data in deriving models that are transparent at the same time. Before that, we were working on aerospace systems, and specifically what's called built-in test design. That is a method to test the aircraft or systems of the aircraft that are critical in the aircraft operation. I'm a chemical engineer, so naturally we chose a heat exchanger where we can actually explain the physics and understand the transport phenomena and heat transfer overall. The heat exchanger in an aircraft is actually a very interesting application of a heat exchanger because it operates at very different environments when the aircraft is landed or when the aircraft is flying 40,000 feet at 40,000 feet, when the aircraft is flying over, I don't know, Sahara or a desert, or where the aircraft is flying over a very clean environment. And fouling is responsible for lack of performance, and in the pack, the pressurized air conditioning kit that is responsible for the air quality inside the cabin. I'm showing two examples of heat exchanger, a clean surface and a dirt, dust, debris surface. As the heat exchanger fouls, what aircraft or airplane companies do is actually they replace the heat exchanger every certain number of hours. That's very inefficient. And the idea was that if we have good understanding of the heat exchanger, its model, its occasions, and everything else, can we use that to actually build models that derive understanding for what how fouling progresses with time, what's responsible for fouling, and use that to perform prognostics. That's in essence an application of symbolic regression inside a very large model of partial differential equations. I will elaborate that later on. So physics for machine learning has many flavors. Different people define it differently. It could be a physics-informed neural network approximation of PDEs. I think your group has done great work on that. It could be symbolic regression, where we're using evolution theory to develop relationships that describe the physics and discover the real physics of the process. Sparse regression, when we actually know all the components that go into the physics, but we don't know the form in which they're combined. And then other types of hybrid models and surrogate models. And what we are trying to accomplish is to have models that are explainable to the process and, generally speaking, agnostic to the process, and work across systems that are glass box and human interpretable, so that we can support decision making. And they're, relatively speaking, cheaper computationally, so you can actually deploy them in systems like aircraft, where computational capability is very limited. So with that, I'll start with work by Ben Cohen, one of my graduate students. And actually, the first paper is what initiated this invitation and this discussion and this connection. Where it's the first sample of his work that focuses on genetic programming for discovery of partial differential equations from scarce noisy data. I follow Yang LeCun, if I pronounce his name correctly, on LinkedIn, and Yang LeCun is actually the chief AI scientist for Facebook, and he's advocating differential programming, and there is so many words or different language for the same thing, differentiable ODEs, differential neural networks, and so on. And there's many tools that exist. I'm going to cover a few quickly here and a few more in more detail in the next couple of slides, and then I'll focus on what we do. PDE find is a data-driven discovery of partial differential equations that's very sensitive to noise and scarcity of data, but it's very fast. SGA PDE is a symbolic genetic algorithm for discovering open-form partial differential equations that suffers from the same disadvantages. Cindy, in the form of chemical engineering, in the field of chemical engineering, has seen big success. It's sparse regression, meaning you know the vast majority of correlations or phenomena that exist in your system, and you're trying to find the best way to combine them using very basic combination methods. Deep mode is deep learning for model discovery in noisy data, and Disco PDE, if that's our final name, we haven't decided, it's our method. The difference of our method compared to other methods is actually that we chose to integrate the differential equations and estimate the parameters, which is very computationally expensive, and I'll show the advantage and disadvantage in what we do, but it's based exclusively on symbolic regression. So goals is the robustness of data scarcity. The significant cost in time is a disadvantage that we need to pay attention to. And we're asking what can be done to improve interpretability and discovery as opposed to neural networks or black box models. So the opportunity is to automatically discover governing differential equations from noisy and scarce data, and that's what we're trying to accomplish. I guess we work on symbolic regression, so I'll go through that very quickly. As I introduce symbolic regression, I usually explain that parametric regression searches a parameter space for an optimal set of parameter values, whereas symbolic regression searches for a symbol space for an optimal set of symbolic expressions. It uses evolution theory, mutation, crossover, and so on. We'll go through a few of these steps as we move on with the slides. And it's based on genetic programming, whereas in sparse regression, which is not too dissimilar, we're using sets of basis functions, as you would call them, of arguments that are good descriptors of a process, and then we try to find optimal ways in which they're combined without the extensive operations of genetic programming. Weak Cindy, which is, you could say, a competition or something that has been established as a very, very strong approach to actually approximating dynamics, nonlinear dynamics, is focused on sparse identification of nonlinear dynamics, and specifically weak Cindy creates a weak formulation that introduces smooth test functions compactly supported on the space of the state space of the system that we're interested in, and shifts the derivative calculation from data to test functions in the form that's shown here, with error depending on the selection of the step size in data and the accuracy of the integrator. Another approach is PINN, physics-informed neural networks, that we actually adapted, and we're working on adapting to symbolic regression as well. The traditional application of PINN is, when I realized the concept, I was actually so excited with it. Develop some form of neural network and take advantage of automatic differentiation to generate derivatives, and that derivative is constrained to the actual PD of a system that could be known or unknown depending on the application, and could be combined with the data as well. So you could discover the actual PD or the coefficients of a partial differential equation in what's called inverse PIN, or you could just discover neural networks that are natural integrators of the partial differential equation, so that you don't have to integrate the partial differential equations to a large-scale system. You just solve the neural network that is actually the approximation of the integration of these equations. The error depends on the quality of the surrogate and not necessarily on the data, and methods used on normalization to choose most important physics, and could have several passes and alternative direction optimization scheme that also works. So we'll see some application of PIN the way we did it as a benchmark for what we're trying to accomplish in a similar fashion through symbolic regression. So our approach is actually trying to discover the governing equations. It's actually, our focus is actually discovering the real equations, and we focus more on how accurate we are in discovering the equations than the computational cost or the benefit. I'll go through this left-hand side of the slide step by step in the next slides. I'll just introduce the problem statement, the simplest form of the problem statement, and then we'll move on to more advanced problem statement. An isothermal plug flow reactor is a set of partial differential equations. In this particular case, we call that accumulation of the concentration of species A as it goes through the reactor. This is a classic form of a diffusional term, and this is a classic form of convection term, and this is the classic form of a reaction, in this case, a certain order reaction of expressing the concentration of A in the reaction. It comes with an initial condition and a set of boundary conditions, as you would expect for a partial differential equation of this form. So the question is whether we can actually discover this equation, and the way we'll do it is we'll create a black box on the right-hand side of the equation. So we'll assume that anything that relates to reactions or spatial effects inside the reactor are unknown. We will accept that there is an accumulation term and there is something that needs to be integrated in time, and the rest of it has to be discovered, but it will be discovered by accepting that we are chemical engineers and knowing that this is a chemical reactor that has certain phenomena that are always present. So the way we do that is we start with a primitive set and an argument set, as you classically do in symbolic regression. The argument set is very wisely chosen, and it's wisely chosen because, as I said, we accept that this is a chemical reactor. So in a chemical reactor, we anticipate that there will be diffusion, there will be convection, there will be some form of reaction, and there will be some initial concentration for species A that's being reacted. And the primitive set will keep it simple because we don't anticipate.
Hi, George. Can I ask a question here on the argument set? How do you know about the nonlinearity? Because you could do CA, CA square, CA cube, and so on, or it could be another nonlinearity, like a sine of CA. How would you? Is that a drastic assumption, or is it something that because it worked in the past, you will do the same? But then you never discover something new if you do that.
So we'll see. In this application, we're not trying to discover something new. The new that we will discover lies in the kinetics. But if you were to say that this is a reactor, in a reactor, you only have this phenomena. You have diffusion, convection, accumulation, and reaction. So we will focus our effort in actually identifying, and we focus our effort in identifying the reaction term later on. In this case, you can say that what we're doing is not too dissimilar than just sparse regression, because we have defined the system exclusively, right? The solution here exists in the argument set that we chose, right? So there is
right. But no, my question is so because I don't know anything about reactions, but the reactions that you expect a quadratic up to quadratic nonlinearity. Is that comes from your disciplinary knowledge, let's say?
That is correct to some extent. We worked with reactions that have diffusion constraints or equilibrium. So I don't know if I present it here, but we definitely have it in the paper where we're trying to discover reaction kinetics that are a little bit more advanced. This is the toy problem, and we will advance it as we move forward. In the toy problem, we pretty much overdefined everything, so we pretend that we know everything. And you're right in that context. That there isn't much to discover in symbolic regression, but this will advance as we move on with slides.
So there's a prior bias. There's a prior knowledge. Yeah.
And I think the main principle of sparse regression in the way Cindy does it, for instance, is the same, that you pretty much have full awareness of what's going to happen. You just don't know in what's important and what not. So the first 3 slides here show how we identify separate what's important from what is not. And then we'll explore how this can be combined further. Okay?
Yeah, thank you.
So GP hyperparameters, mutation, probability, and crossover, and also the inclusion of the expression as we defined it earlier. And we will use these 2 sets of data. This is the concentration of A at the outlet of the reactor as a function of time. It's 0 for while the A goes through the reactor but hasn't actually hit the exit of the reactor, and then it increases slightly, and then it reaches some steady state. So this is the dynamic part. The steady state is really what is the design equation of a plug flow reactor at steady state, before and after. So we'll start by creating a population size and expression trees. Our argument set is really the convection and diffusion terms, as I mentioned. And what I'm showing here is a erroneous first approximation that symbolic regression could do, take the convection term and multiply it with the diffusion term, what I'm showing here. And this happens through a tree that looks like that. So CA minus the product of CAX times the second order derivative of CA with respect to X. So that's not the correct answer. This is just an example of what symbolic regression would do in this particular example. Start combining all the basis functions with the primitive set that we defined earlier. So we initialize the population, and then we build a model based on that. So we'll assign parameters to CA and to the term that we just discovered, and we can have more than 1 parameters. And then in our case, what we do unwisely in a sense, but at the same time it comes with benefits, is actually we build that model, we assign parameters, we integrate that model in space and time, and then we test it against fitness metric. In our case, the fitness metric is the Bayesian information criterion because it penalizes overcomplicated and overfitting data. So
excuse me, can I ask a question? Quick question. This is Panostinis from Pacific Northwest National Lab. When you say population, what does this population have? What are the components of this population?
The population is here. The
right.
population, the population is the number of evolutions that will allow for the first layer of symbolic regression. And,
okay. Okay. So with those operations that you have
with
defined,
what we allow.
Okay. And that population, the 100 of them will be chosen, how they will evolve, at least, you know, the suggestions that you will make will be what, based on some combinatorial argument, or?
So how we use deep, and how deep actually decides to proceed is unknown to me. And
okay.
There is center randomness, and we actually do this several times. I'll show the percentages. So we do it more than once, and we keep the winners over the majority of the cases. I'll present this more.
All right. Yeah, thank you.
So once we have a solution, then we go back to symbolic regression. It will do some form of evolution through crossover and mutation. It will start actually creating child trees from the initial population, and with that, this child trees will build a new model, which will send for parameter estimation, integration, and the fitness evaluation. And eventually what it will do is it will find something that fits the data. That is the easy part, finding something that fits the data. The question is whether we found something that is actually the equation that was originally used to derive this data. And all this data were derived by the original equation, adding noise. What I'm showing here is the final result. So a discovered model for this particular case with two different initial conditions, boundary conditions for the component A, and the squared error that is practically zero throughout. The beauty of it is that you really used only the exit reactor concentrations, and by integrating, we introduce computational load, but we substantially reduce the number of sensors or the information that we require. So we did a sanity check, and we took a plug flow reactor as a continuous stir tank reactor. Plug flow reactor equation is the one that includes diffusion, convection, and the reaction on the right-hand side. The CSTR is a much simpler equation. It's just an ODE actually. It's a function of the initial concentration, the concentration in the reaction term, the concentration at the outlet in the reaction term. You can assume that there is a dCdt on the left-hand side of this equation, but the dCdt is assumed that it's always there. There is always accumulation in any of the reactors. So we do several trials. I think Ben is there to remind us how many, but 95% of the trials discovered this equation that is close enough to the equation that was the ground truth. A small difference in the parameters are due to the noise that we added and the parameter estimation that we used. And in the CSTR, the same. So we gave the exact same argument set and primitive set, the exact same framework to two different sets of data. The one was from the PFR and the other was from the CSTR with a little bit of noise. And that's the first step, as I said, there's a sanity check. It discovered the correct equation for the plug flow reactor, it discovered the correct equation for the CSTR. So it works in the context of one reaction and identifying the dominant phenomena that exist in a particular system. And as I said, so far, this could be done with sparse regression. There's nothing here that sparse regression couldn't have done. And so then we actually took it one step further and said, okay, no reactors, very few reactors are actually isothermal. They usually incorporate mass and energy balance as well as a chemical reaction. And in this particular case, we chose a chemical reaction that has a combination strategy that follows the Arrhenius expression. What I'm showing here is when we use this as a constraint. So this was provided to symbolic regression, this KT. That is a classic Arrhenius expression on how reaction kinetics evolve. And in many cases that's known, but you don't know the dominant phenomena, the transport phenomena inside the reactor. In another work that I'm not presenting here, I'm actually presenting it soon at a conference. We actually use the method of characteristics to simplify the way we do the integration and ask the framework to identify the parameters and the form of the Arrhenius expression as well, which is an overkill because the Arrhenius expression is pretty much always the same in our field, in chemical engineering. So this is co-evolution of three expressions. The one describes the mass transport, the other describes the energy transport, and the other describes the chemical reaction. And in this particular case, we forced this combination to exist through this KT. So this is our combination strategy. So this problem is reduced to a problem of identifying S1, S3, S2, and S3, and figuring out what these forms are. So the ground truth for that was that, and what we discovered was, about the same. So at the computational cost, because now we're integrating a system of equations, it's only 2. Imagine what happens when it's 100. We actually discovered the ground truth of a system with little knowledge of what it is, except for the fact that we have a very well-defined and a domain expert driven argument set, and a combination strategy that is derived by kinetics that might be known for.
I have a question. Where does the K of T come in? I know it's coming in the prediction, but how does the system know about K of T?
So in many cases, if we were to assume that there is a reaction A to B, agnostic to.
Oh, I see. Actually, I see it. Sorry. I see it in the chemical reaction. You have a triplet: Ca square K of T. So they could be multiplied. Yeah. Okay. I got it. Yeah.
Okay.
Yeah. Sorry.
So then took it one step further to explore the Berger's equation. It's a classic benchmark for these types of systems. And in this case, we're actually exploring how we compare to weak Cindy and deep mode, and how we compare in terms of the error in the parameter estimates, and how we compare in terms of computational complexity. I'll be very honest about the benefits and pros and cons of our approach. So we discover the Berger's equation using our approach, and what you see here is the error of parameter estimates as a function of the number of sensors, how many sensors you have in the axial direction, and how many samples you collect over time. So weak Cindy stops predicting anything after 46 sensors. Deep mode fails after 8 sensors. We can go all the way down to 1 sensor because we integrate and we measure everything at the outlet and get the accurate, correct expression. What all these data points show is when we actually get the correct type form of expression and how accurate is the parameter estimate of parameter estimates. So the great news is that we can go down to almost minimal number of sensors, and in a separate work, it's actually that I don't have in the slide, we're actually showing that it's very insensitive to noise as well, mostly because we're integrating over the length of this system. And the benefit is simplicity or requirements of data. The disadvantage is the time. So you can see Cindy, that's why it's so popular. It's actually extremely fast, whereas deep mode and our approach are very slow, and our approach is about 1 order of magnitude slower than deep mode, and many orders of magnitude slower than weak Cindy. The reason for that is the fact that we're doing integration. We have a plan to address this that I will explain, I will discuss as we move forward. So the plan is actually inspired by physics-informed neural networks, and Nazi Aslam is working on several projects, but one of them was, okay, let's figure out how to use PIN and how we can learn from what it does to actually apply it to what we want to do. So we use the NVIDIA Modulus tool that I think you guys have contributed to some extent in the key ideas. The key idea, as I mentioned it earlier, is really develop a neural network, take advantage of large-scale optimization solvers and automatic differentiation, and then Monte Carlo integration for loss formulation against the PDE that is known, or against the PDE of which the form is known but not the coefficients. And it has the advantage of parameterizing geometries. It's super efficient. So when we compare times and efficiency, it's not an apples to apples comparison. It does causal training. It parallelizes very well. It's using GPUs, and it's reducing substantially the computational cost of all of this. And it's open source and user friendly through Python. So the idea was what inverse pins do is they have a loss function that is a combination of the data, of the loss function of the data against the data, and the a partial differential equation for which we might know the exact form, or we might know the width coefficient, or we just might know the just the form. And so we took the same idea and we said, okay, what if we can actually do symbolic regression to identify the parameters of differential equations, assuming that we know the form or some aspect of the form and we know data. So in a similar fashion that PIN does with neural networks, we explore whether symbolic regression, we can do the same with symbolic regression. And the whole idea was, if I can do the same thing, and if I evolve a function with symbolic regression that then use automatic differentiation, which I can in the same fashion that neural networks do, whether I can simplify the problem and I don't need to integrate anymore, because the symbolic regression, the function that they involve through symbolic regression, is actually the integral of the partial differential equation. So I avoid integration. The other beautiful thing here is that if I do it with symbolic regression, in some systems like a plug flow reactor, the method of characteristics actually can give you the analytical expression for just one equation. So we could, we're exploring whether symbolic regression will actually identify the real solution to the PD, which is the most exciting part in my view. So this is a table of what we did for a very simple equation. This is the equation, just a simple convection term and accumulation term and a first order kinetic term. This is work in progress, so we'll explore more advanced systems as we move forward. 5% noise in all the cases. We did it with inverse pins and symbolic regression, and the predicted values of the coefficients. In this case, pin knows the form of the PDE, but not the coefficients, so it has to estimate those. The predicted values are very close in all cases, a little bit more accurate from symbolic regression, but we're comparing apples to oranges here in all aspects. So I wouldn't pay too much attention to the details of the accuracy. What I would pay attention is how pins and symbolic regression do it. Pins will create some neural network that has, I don't know, some 7,500 parameters and fewer points, fewer parameters, and it takes less time than symbolic regression, but keep in mind that this is parallelizable on a software that's designed for the specific GPU and so on. And so we lose time. We are slower, but comparable. And the way the loss works is like that, very fast, actually. Pins will find the correct solution or a very small value for the normalized loss, whereas symbolic regression will take a little bit more time because it has to evolve and test many unwise combinations of the argument set, and it will also fail in some iterations. But what we discovered and what's not in this slide is actually that the solution that symbolic regression finds in this simple case is actually the correct solution, analytical solution to the PD. And that's very exciting if you think about being able to find analytical solutions to PDEs, or being able to explore or discover the truth in a system as opposed to a deep neural network or slightly deep neural network with several parameters.
Excuse me, can I ask another question here?
Yeah.
Because you used a wisely chosen word. You said unwise combinations. So is there any way for this training, for the symbolic regression, to make it wiser? Because I suppose this is some kind of a genetic algorithm, right? Like before.
So the way I understand it, and we'll have to ask the students for that.
Yeah.
That's a good question to the students because I don't do it personally, right? I call it you massage it. You massage it in the sense that the depth of the tree, the number of mutations, the hyperparameters, and everything else that you have control over is something that you can manipulate to make symbolic regression do what you want. And we usually show the successful result. You don't know how many weeks the student was massaging this to get it right?
Right. So my question is, have you somehow studied how sensitive it is to the choices of the depth of the tree, the hyperparameter and other hyperparameters? Because I think that, that could accelerate, right? You see, you use only 5 and 3 parameters, but it takes about 100 seconds, which means that it has to go through a lot of different
unwise
choices. Yes.
Unwise choices. Yes.
Yeah.
It's an interesting point, and I'm pretty sure Ben and Asia have done this, but we never formalized it in an analysis that shows how sensitive it is to the user, to the expert who's actually deploying that. That's a good point. That's a good pointer to what we should do to explore how it grows, and also if there is a recipe of heuristics that actually simplify this exercise,
right,
for a new user especially.
Yeah, thank you.
So I'll switch gears. I'll remain in the same context. I'll switch gears to the work by Effie Safiku, who actually works on the heat exchanger problem. And here is something slightly different, is whether we can use data to augment physics-based models. So you could say this is physics-informed machine learning in the sense that the physics are actually naturally embedded in the exercise. Or you could say that this is a way to estimate physics from the parameters that exist in the model. So I'll explain this in more detail as I move forward. So we have a heat exchanger that is 125 differential algebraic equations after discretization, and we use central finite, I think finite volumes here to discretize. And we have 2 hard sensors and uncertainty that goes into the system in the form of moisture content and cold temperature, and we have 1 fault that will evolve with time. And we took an asymptotic form, but we could take any other form. An asymptotic form is actually reasonable for how fouling and thermal fouling resistance evolves in a heat exchanger. So that is what we don't know, and let's assume that we have the perfect model for the heat exchanger. I mean, we will work with noise and uncertainty that we will inject in the form of Gaussian distributions, but we're assuming that the rest of the heat exchanger model is correct, and we just don't know faults. So we're trying to do fault prognostics. That means that we'll estimate these functions so that we can use this function of how fouling evolves, so that we can predict the future, the fault as it evolves in the future. We do this by using symbolic regression in 2 ways. The one is an inferential sensor that actually evolves. I'll show how it's developed. It's earlier work, and it's not really physics-informed machine learning. It's a symbolic regression application that uses information theory in its objective function to maximize the sensitivity of a system with respect to a specific fault. I'll explain that in the next slide. And then we'll define anything that relates to the fault, fault and failure baseline, Monte Carlo simulations over uncertainty and noise, and of course the system model and parameter ranges for the fault and uncertainty. And then symbolic regression will evolve this function inside the model. So we'll estimate this fault function as a form of time relationship in this simple application. And with that, now we have a function for the fault, so we can predict the remaining useful life. And so one question is how we create these inferential sensors. And these inferential sensors are actually, I'll run through this slide because it's a little bit less relevant than the next one. It's based on sensitivity analysis and estimation theory that develops some form of optimality criterion. In this case, we used DS optimality. We used also D optimality. These are traditional criteria for model-based design of experiments or optimal design of experiments. The sensitivity analysis formulated into the Fisher information matrix, of which we take the determinant, and that determinant maximizes really the sensitivity of the outputs with respect to the fault, in this particular case, the parameter that describes fouling. And the physics-informed component, the machine learning component, is that what we will do is we'll evolve a genetic program that builds a function that is fed to the system model that is integrated to calculate hard sensors, or not sensor predictions. but we're not going to use the sensor prediction. We're going to use this inferential sensor that we developed because it's more informative. So the whole idea is, can we build a genetic program, a genetic program that builds a function that is fed into a system of partial differential equations, so that we can identify what the fault is. The other way you could do that is you could assume that you estimate parameters with respect to from all the measurements. You find the best parameters from all the measurements, and then you fit a function to that. Instead of actually doing a parameter estimation twice, we do symbolic regression. We explore how this evolves with time. So I'll just show you all the results. What's shown here is the function that we're trying to estimate, the fault that we're trying to estimate, what the function that we estimated looks like when we use only the green area of data. So we assume that the first 50 minutes we have only this data. We build a function based on this data, it's the green line, and then we use that line to predict when the fault is going to happen, and also when the system is going to fail, the rule. When we have very little data, it's not working. Obviously, there is not enough information for the system. As we start keep adding data, we're actually getting closer to predicting when failure is going to happen. This is the future, right? Outside of the green box. And also we get closer to estimating the correct function for thermal fouling resistance. More data, more accurate function, even more data. When we get really close to failure of the system, we have the perfect function and the perfect estimate of the remaining useful life of the system. And if that's can be presented in a system, in a rule error as a function of iterations, very quickly we get very, very close to the remaining useful life, correct remaining useful life estimates, and also the error of the model after the first 5 iterations, as I presented them, is practically 0. So it's a very hybrid predictive approach where you integrate or infuse data into physics, and it's very robust in performance. It's extremely computationally expensive because symbolic regression does all its unwise stuff, and then you expect to anticipate to integrate that inside DAE of 125 equations and variables in this particular case. I don't have much time, so I'll try to run through that. This is the last component. This is where we did the manufacturing application, and there we just said, let's just do symbolic regression with little knowledge of what the model looks like when there is no model, but we have an understanding of what the basis functions should include and how that works. And the idea was that identify toolware from other measurements, and toolware usually has a shape like that. So you know what shape you're dealing with. There is an initial wear, a steady state, moderate wear, and accelerated wear. This is what toolware looks like as it progresses through these stages. And we identified variables that are important out of the machine settings. And we identified through an analysis, sensitivity analysis of each one of those. So the questions that we tried to address were whether we can form a generic tool for systems like that, and how we can capture the physics of the process in the model that is entirely data-driven otherwise. We did that again with symbolic regression, and it could be either sparse regression or genetic algorithm. We followed mostly the genetic algorithm approach, but we also used Alamo, that is more like a surrogate modeling approach. And generally speaking, we come up with models that look like that, have little physical meaning except for the functions that it's using. Just to introduce Alamo, it's also popular in chemical engineering. It's automated learning for algebraic models. It's not formally symbolic regression. It does many of these tricks, but it's not. It's based on global optimization and on global optimization combination of functions. And we use also GPTips, the genetic programming toolbox for identification of physical systems. That's more of a classical symbolic regression. This is also an exercise of comparing different tools in a sense. And we also built 2 models in the beginning, a toolware model that focuses on predicting toolware from machine settings and cutting conditions and time. And then we built toolware rate model, where we thought that it might be easier, instead of trying to predict that curve, to predict the derivative of that curve, the logarithm of the derivative of that curve, as I'm showing it here. And in both cases, we tried Alamo and GPTips. We use 33 different data sets. NASA has a very wonderful data set of this system, and very variable. If you're into manufacturing, which you're not, could explain how variable this is, but this covers a very large space of manufacturing application. As I mentioned, we actually created a correlation matrix, the matrix, to identify what are the most important variables, and it's the first 5. Here, spindle speed, width of cut, depth of cut, feed rate, and number of teeth. And we took that one step further. We identified data sets that actually tell us a little bit of a story of what's important. This is the spindle speed, this is the feed rate, and how different combinations of these variables actually affect the tool wear as a function of cutting time. And one step further, and trying to relate these variables to things that are known or understood by domain experts in manufacturing, like chip thickness and hardness, and identify relationships in that. All this exercise led to this. Develop basis functions that are informed in the sense of, for instance, the product of depth of cut, width of cut, and feed rate. It's what's called material removal rate, or the material removed. That's the same variable times the total time, or the mean chip thickness and the distance. So if you look at all of this, this relates to the question that Panos asked earlier. This is nothing that symbolic regression cannot identify. What you do by providing this as basis functions is actually you massaging the system. You say, use this if you're interested in that, instead of trying to discover those, because I understand that these variables are important in what I'm trying to accomplish. We use Alamo in GP tips, and Utsa would tell you that we had great success in the R-square of how we fit. You see the function, it makes no physical sense. It's not anymore something that is a governing equation of a system or anything else. And then in our testing set, you see that we didn't perform that well. So we realized that although we get good R-squares and so on, and models that are to some extent descriptive of what we do, we didn't actually get a good fit of the data with our testing set and so on. Then we looked at it again and we said, okay, tool wear is actually a function of tool wear. When I'm here and I want to move there, what will happen to tool wear depends on where I am in the tool wear range. So we did what we think is the first recursive model for symbolic regression. It's actually using the prediction of the previous value to predict the evolution or the progression of tool wear. And when we did that with GP tips, we cannot do that with Alamo because it's not completely open source and we cannot manipulate the software that much. So we use the same approach, physics-informed basis functions, also a lot of massaging in all the hyperparameters of symbolic regression. And we got a model that's actually expressing tool wear in the next step as a function of tool wear in the previous step, starting from 0 and predicts as we go on. And also in all these cases, it's using functions that are very reasonable as a function of the time, or as a function of the product of time and spindle speed, and of course as a function of tool wear. And suddenly all the predictions look much more accurate and reasonable in testing sets and validation sets and so on, because we actually injected something that's fundamental in understanding of the process, that is, the tool wear is a function of itself. So symbolic regression methods provided the simple process models, and we did this recursive model for symbolic regression to have a very good model, much better model than just trying to predict everything from time 0. So with what we learned, my goal, as I said, is to enable the discovery of physics from data, and I would like to someday automate the teaching of basic engineering principles through the extraction of those from data and domain expert knowledge. Explore data-driven approaches that provide unique new insight to process systems, as we did in the manufacturing application. And how did we do against this goal? Some methods work. Computational complexity is the elephant in the room, and we try to solve that by evolving the integrals and leveraging automatic differentiation, symbolic differentiation, and so on. Symbolic regression can get lost as system problem size increases, so we're trying to explore that. There is a beautiful piece of work that we did with a method of characteristics, when you actually simplify the problem into something that's more easier to compute and more determined in terms of, or defined, better defined, narrower defined in terms of how it's presented to the symbolic regression algorithm, genetic programming. Hybrid approaches that fuse symbolic regression, scarce regression, PN might be better suited. So in many cases, we're trying to figure out whether we're doing symbolic regression or scarce or sparse regression. And there is always an interplay there. And the mathematical manipulation of the equations are extremely beneficial, for instance, when we apply method of characteristics or things that we know simplify, approaches that we know simplify the governing equations. But that would imply you have a good understanding of what the governing equations look like. So right now we're working on simplifying, reducing, eliminating the need for integration in the ODEs and PDEs and DAs. And we're also asking the question of, we use the sundials solver integrator, which is really the most expensive and accurate integrator for PDEs and ODEs and DAs. We're playing a little bit with, as I call them, sloppy integrators to see if it makes a difference if your integrator is something like explicit Euler or something very simple and it comes with error, but you fit the functions anyway. So how important is that error? That's something that I hopefully will have answers later on. So with that, I think we left us a few minutes for questions. Thank you very much for the invitation again, and I'll be happy to answer more questions.
Thank you, Professor Bollas, for your great presentation. Now we open the floor for questions, but first of all, I have questions for you. Can you go to your slide 29? I think first you talk about not a gray box or not a black box identification. You were looking for the value of parameters in your equation, the first problem. So you use symbolic regression and incorporate pins, actual physics in your algorithm to find the value of parameters, that we could do it with solving the inverse problem in pins. But here you are, actually you have a part of physics that you don't know anything about it, and you have data for like the right hand side of your equation, right? So you are using the
I went over that a little bit too quickly. So you can assume that, I mean, the traditional way of doing this would be you calculate the theta f that best fits the data, either with the original hard sensors or with inferential sensors. That's less of importance. You calculate of importance. You calculate the theta f, and then you have a time series of theta f. It's progressing with time, and then you try to fit a function to that. I don't know why we didn't choose to. I know why we didn't choose that. That because we wanted to explore how computationally efficient it is, and this wonderful idea of actually building a model inside an existing model, of actually discovering it in real time.
But I think it would be very expensive in terms of computational cost, because we are looking at this problem differently. We are using Pin's model to, I don't know, to fit a function instead of the missing part. And then we use symbolic regression in one try to find the analytic form of the analytic expression of that part. So, but here you are using the symbolic regression at each iteration to find the exact the analytic form of that missing part and put it into the equation, and computing the loss, find the loss, and then again you go through the symbolic regression part, which is very computationally
so symbolic
expensive.
regression in this case, symbolic regression is actually reduced to very basics, very shallow trees, and very few parameters and so on, and very few functions. So it's not that expensive. It's actually not. So one of the things that we wanted to explore in when we did this is if it will ever solve, like if it will ever find anything, or if it will get lost and will come back 1 week after and still searching for something. And it actually solves in minutes, so it's not that bad. We take advantage of automatic differentiation, automatic calculation of the Jacobian, and all of that stuff. So it's actually very efficient, or most efficient. Yeah. But I do agree that you could do the same by estimating parameters and creating data series of parameters as a function of time and time series of parameters, and then fit symbolic regression to these parameters. That could be something. It's more of a mental exercise of whether we can do it and whether we see benefits in it. In real-time application, we do see benefits in it, and when you have very few data points for theta, you're doing parameter estimation over R, and then you'll do symbolic regression over that. It's a two-step process as opposed to one-step process. So it's not entirely black and white.
I will put our recent paper, the archive version of our paper. You can look at it because we are looking at the same problem differently, and I think I believe it would be better to compare your method with our method. Like using the pins. Yeah. Thank you so much.
So maybe we should compare our method with their method.
Yeah. We can do that. Yeah. Either way works. So
I think Juan had the question.
Yes. Oh, hi. My name is Juan Toscano. I'm a PhD student here with Professor George Kanadakis. It was something like related to what Panos was saying about like some kind of guiding the model. Like, is there a way to how hard is to add more constraints? Because did you try to analyze something like some type of combined with some type of dimensional analysis in your model? Because I haven't played with this, but for example, in some problems with rheology, and if you see like all the models that they use to model their viscosity, they're usually lower order because you can get polynomials, like say you can go up to x to the 10th, but then it's really hard to find like a physical quantity that could be non-dimensionalized to that value, right? Let's assume that you are like, I don't know, your velocity to the 10th, then you have like to get a coefficient that is L over T to the 10th. So it's really hard to find how to relate it with a physical parameter, because the idea of, or that's what I understand, the idea of doing symbolic regression is to obtain functions that are a bit more interpretable than deep neural networks models, or at least that's what I understand that was the motivation. Did you try to, or how hard it would be like to combine it with dimensional analysis to guide a model?
The dimensional analysis would be definitely one way to approach this. I think I'll send you or George the paper, and he can share it with you, where we did the same plug flow reactor problem with using the method of characteristics, and it was substantially faster and more efficient. It's not dimensional analysis, but it's actually also along the same lines, really working with the equations to derive a set of equations that you're trying to predict. That's the simplest form that's presented to symbolic regression. So less work for the symbolic regressor. So I completely agree with the context of what you're saying, in the sense that put all the work on the user, on the person who's doing the symbolic regression upfront to find the simplest form that of equations that we're trying to predict, and then leave less work for symbolic regression.
But actually I was saying that what if we don't know the equation? Because I was saying, is there a way like to penalize the combinations that lead to things that make no sense? For example, as I said, for example, velocity to the 10 may not make sense physically. So you penalize going to that values where the dimensions do not agree.
So it depends on the, now I understand the question. So in the majority of tools, whether it's deep or Alamo or whatsoever, you can penalize, never allow the exp of the exp to happen, for instance, right? And penalize things like that. Because when I see a result that has the exp of the exp of the exp, we used to work with Eureka, and now it's not open source, now it's called something else, robotic or something like robot something. And Eureka would often give us the exp of the exp of the exp. GPTips also give us the exp of the exp of the exp. And then you're asking yourself, have I ever seen a phenomenon as a chemical engineer where we get the exp of the exp of the exp of anything? And the answer is no. But this is what it wants to find. So there is ways, depending on the tool, where you constrain the power that you allow or the complexity of the specific evolution that you allow. This is a little bit, these are good questions, and your group is better suited than our group to actually address these questions or this field, like really make it so that we have symbolic regression that actually is very very tuned to what we want from it instead of just allowing it to evolve the way it evolves.
Yes.
If I can just follow up on Juan, you can continue, but just on that thought that Juan had, because I remember a paper by Winkham Liu from Northwestern where they were doing some laser ablation for additive manufacturing application, and they didn't know the equations, and it was kind of what you presented, George, except they were actually doing dimensional analysis. And in the process, they identified non-dimensional groups that turned out to be very important. And then they guided. They were not doing symbolic regression. They were doing then neural networks, but they guided neural networks using their dimensional groups.
He doesn't know what he's talking about.
Hello? Somebody said. So anyway, so that's the.
That's exactly what we did in the manufacturing application, where it wasn't dimensional analysis; it was domain expert knowledge, right? Material removal and this and that. But at the end of the day, with the two tools that we use, Alam or GP Tips, you can provide as much domain expert knowledge as you want. It's gonna decide whether it wants to keep it or not. I don't know how you have control over like forcing something to exist, except for just providing as a basis function. Possibly you can include it in the objective function, or you can force it inside the code to actually exist no matter what. But at the same time, when you're giving a basis function that you think is superior and it chooses something else, maybe it's trying to tell you something. I don't know. I don't know what the right answer is there.
Yeah. Sorry, Juan, you want to continue?
No, actually, we're just gonna thank him for the answer. But yeah.
So since I have the floor, maybe one other question is, have you or another group has tried to combine neural operators with symbolic regression? Because this will give you a description of a plurality of processes, not just the one specific process. It will also, the issue of fouling on the heat exchanger could be addressed, because of course you will subject this to different conditions, and then the neural operator will learn that, and then you turn that into with symbolic regression into equations which don't have fixed coefficients, or they can have variable time-dependent coefficients and so on. So in other words, it's a more abstract level working with neural operators. I don't know if you are familiar with that line of work, but it's that's something we did beyond pins, and now everybody's trying to use neural operators. Combine, so the new thing here to combine neural operators with symbolic regression, for example.
So I'm familiar, and we've been toying with liquid AI from MIT that is actually along the same lines, I believe. I don't know if you're familiar. Like
yeah, I know it. Yeah.
And I never even thought of actually combining symbolic regression using neural operators. That's actually a very interesting suggestion. How on earth would we do that? That's 2 layers of fitting. It's an interesting suggestion, but no, we haven't done it. It's we play with liquid AI as we're exploring. First of all, there are sloppy integrators, because that makes it feasible to begin with, and then the whole architecture of how it's doing things, but not much more than that. But it's a good suggestion for us to explore.
Thank you so much. Are there any other questions for the speaker?
Mario has go ahead.
Yeah.
Yes, thanks, Professor Bollas. It's a very interesting talk. I'm Raj from Brown. I just have a very naive question that for symbolic regression, what package you used here? Because you mentioned you have to do a lot of parameter tweaking, and it's not robust in terms of training. And so what package you have used for this?
Depending on, the heat exchanger and the manufacturing, we're using, both used GP tips. That is, the reason for that was that the rest of the models and stuff were all in MATLAB, and that is very easily amendable to MATLAB, and it's a very open source. So in the heat exchanger application, we really infused information theory, the Fisher formation matrix, the determinant, and everything else into the calculation of the objective function. So we needed complete access to that. In the first work that Ben is doing on symbolic regression for just discovery of physics, we use DEEP. I have it right here. And in the manufacturing work, we also used Alamo, the automatic learning of algebraic models. That's the stuff that I'm presenting. I'm pretty sure we tested other packages as well, but I don't remember if we had any success with other packages. I know a few that you mentioned already, but for whatever reason, DEEP is very, very robust and very rich in what it does. So it was our choice, and it's also easily amendable to Python, and from there taking over to Casadi for automatic differentiation and so on. So, but that's more of a tool chain question, and it's a good question, and there's so many tools out there, who knows? I'm open to suggestions, actually.
So yeah, I can share my experience. I used two packages. One is the GP-learn and another was PySR. And I found PySR to be more stable and very less tweaking. I think that when I look into the algorithm, so in the PySR, they use simulated annealing as one of the modification, and that is based on the temperature on which you reject the expression. So that is more robust than the GP-learn, because we had a heck of the time with the GP-learn for our problem. So the PySR was very quick, and it doesn't require much tweaking, actually, in other words. So I haven't used DEEP and GP tips, but I will definitely give a shot, like if there is any robustness better than PySR. But yeah, so that was my experience. Just wanted to share with you. So
I think Ben is on the call, and the other students that could comment on their experiences. And again, with DEEP, I remember at the beginning we had all kinds of issues in the parameter estimation component, very weak there. And so we had to go away from parameter estimation and do parameter estimation in Python, and leverage Casadi to inexpensively get derivatives, Jacobians and stuff out of a model. I don't remember. I think I know PySR. I don't remember who used it and when, but that's a good suggestion. That's something to explore.
Lately, I was trying, like in PySR, you can pass a PD as a operator. So you just try, if you can define it as a function, you can pass as an operator. It's not a constraint, but it will be in the pool of the operation which is chooses to do the tournament selection. So that is the one good thing about the PySR. Like this is very customizable. So
yeah, you just gave Ben another month of worth of work. So thank you.
Thank you, Raj.
Yeah. I mean, so we worked on both packages, but we will definitely have a look on these packages you mentioned. Thank you very much. It's really interesting talk. So thanks. Thank you.
Yeah. Are there any other questions? I think Mario.
Can I have a question?
No, I don't have any question. But George, thank you so much for your talk. Raj already shared the same thoughts I have. I recommend you to use a PySR. It is very fast, user-friendly, and not many parameters to tune. But nice talk. Thank you so much.
Oh, thank you.
Elham, introduce yourself and you can ask your question.
Hello, I'm Elham from Brown. I have a question about the last part of the presentation, Alamo method and discovered equation that you showed us.
Can you repeat?
About the last part of the equation, the method that you said, Alamo, and discovered equation.
In the manufacturing application, right?
Yes, the last part that you showed us. Okay, yeah, here. My question is that, for example, there are some softwares that can be used for discovering equations like this part. For example, just take out data and predict these long equations. My question is that, for example, for discovering equations, having this equation, something like this long equation. My question is, generally studying this equation is not that easy because of the terms that they have, or they are complicated. So my point is, for example, for the purpose of discovering equation, as I know, is having a simple equation that's easy to understand behavior of data. But for example, for some cases like this, I don't know how we can use these long equations with different terms to study data. I think it's harder than checking behavior of data, because like studying or understanding these long equations is not that easy.
I agree. My takeaway from this work was really in the context of understanding the problem better and being able to say, okay, what I'm looking for is not just a model that fits 33 data sets. What I'm looking for is a model that fits 33 data sets when the previous value of toolware is known. And it's a slight modification to the problem statement that yields very good results. The value of the equation itself, I mean, you could claim that the operator knows that it's a function of the previous step or toolware value of toolware, or the exponent of the time of cut, or this product spindle speed time of times time of cut, that is actually very important, or a function of the hardness times the previous value of a toolware. These are all gives you a little bit, if you think about it in a recursive manner, you're looking for the slope in different scenarios, right? So it actually estimates the slope in different scenarios, how it's gonna go from one to the other, and for all I know, it's close to linear in all these steps. It's not, obviously this is not a linear model, but it's close to that. So it gives you a little bit of insight of what are the important factors. I'm not going to claim that all of the insights are correct, or that you read this equation and say, now I get it. No, that's not the case. But what I do like in this piece of work is the fact that instead of just trying to fit data, we said, okay, let's look at the data for a second and understand that might be an easier problem than what we're trying to solve. It's maybe it's much easier to predict the toolware of the next step by using the known toolware or predicted toolware of the previous step, as opposed to actually trying to predict the toolware as a time series, all of it from time zero. And that worked very, very well. In that context, there is value. In the context of actually reading this equation and saying, I discovered all truth about toolware in precision machining, I agree with you. It's not that. There's other benefits. If you could do that with recursive neural networks, right? And you could most likely get a better result. One would argue that in the manufacturing domain, because of the lack of expertise and stuff like that, this is much simpler. That's much simpler to evolve and much simpler to use. And it's good enough, but it's not the end goal or solution of all problems. So here it is, we discovered the truth about manufacturing or toolware. It's more about, okay, we actually found an equation that provides a little bit of insight. It gives us good understanding of the key parameters that contribute there, and most importantly, it uses our expertise and understanding of actually I look at the shape of toolware and understand that I have to fit that kind of function. There's many different approaches that would do the same, actually.
Yes, thank you. Thanks for your presentation. Thanks.
Are there any other questions? Okay, I think there is no more questions. So it's time to close this session. Thank you, Professor Bollas, for your great presentation. I am very, very interested in your work and to see how we can compare our results with two different angles of view to the problem. Thank you so much. You can, I think, turn off sharing your screen because we should move on to our next session.
Okay. Thank you very much for inviting me. It's wonderful.
You're welcome. Yeah, thank you for your time.
Thank you. Okay. Bye-bye.
Bye. Actually, you can stay for the next presentation if you have time.
Yeah, sure. I'll stop sharing that.
Yeah, I saw Dr. Jingxian An is here.
Yeah, I'm here.
Okay, can you share? Can you share your screen? Yeah.
Yeah, I'm thinking this one. Can you see my screen?
Yeah, presentation mode. Do you have any video to check if?
Okay. Can you see my PowerPoint?
Yes.
It's okay. Actually, my work is focused on the food science. Machine learning.
Jingxian,
Yeah.
Jingxian,
Let me introduce you.
Okay.
Yeah. So our second speaker is Dr. Jingxian N. He will be giving a talk on utilizing machine learning and phenolic compound analysis to enhance quality control and protect the provenance of New Zealand Pinot Noir wines. Jingxian is a researcher skilled in big data and wine science, holding a PhD from the University of Auckland. She specializes in AI and big data application in the New Zealand wine industry, focusing on quality control and enhancing Pinot Noir wines provenance. Before her PhD, she earned a master's degree from Central South University, focusing on natural product chemistry, particularly extracting and analyzing compounds from pollen typhi. With a 7-year interdisciplinary academic background, Jingxian is dedicated to innovation and scientific advancement. Thank you for joining us today. So with that, you can start your presentation.
Okay. Today I will present my PhD works about utilizing machine learning and phenol compound analysis to enhance quality control and protect the privacy of New Zealand Pinot Noir wines. I will introduce this content from 6 years background and 6 structure, balance the cost and the prediction quality of soft sensors, developing chemical soft sensors for predicting the product intrinsic cues of New Zealand Pinot Noir wines, comparative analysis of New Zealand and South Australian Pinot Noir wines, clarify the relationship between product intrinsic cues, sensory attributes, and chemical parameters, future recommendations. First, I will introduce the background and my thesis structures. Why New Zealand Pinot Noir wines so popular? New Zealand Pinot Noir wines have unique flowers and tastes and fragrant aromas. New Zealand Pinot Noir wines are easy to pair with food and are one of the most difficult wines to purchase. According to the New Zealand wine website, official website, in this year, New Zealand Pinot Noir Vineyard Air and Weighted production hold the second positions, and New Zealand Pinot Noir wine export has ranked third among all the wine weightages. And why are sensory attributes are so important? Sensory attributes are the perceived qualities, which are usually evaluated by the human panelists, which are wildly exciting in the food. So food is usually needed to understand sensory attributes. Common sensory attributes include several areas is appearance data, aromatic profiles, basic taste, mouth feeling, flower attributes, quality indicators, and readiness for drinking. Sensory attributes can determine wine qualities, wine commercial values, and consumer choice. Traditionally, sensory attributes are usually evaluated by human panelists. However, it needed to recruit experienced sensory panelists and to get sensory results rather than get sensory results immediately. And due to this is evaluated by human panelists, so the sensory results is sometimes is subjective, and it is impractical to let the human panelists to evaluate wines on a large scale. So currently, soft sensors are become popular to predict sensory attributes rather than human panelists. Compared to the soft sense, compared to human panelists, soft sensors can provide sensory results fastly and objective, and the sensory results on a large scale. Soft sensors work as a framework which include the input data, which is easy to measure and combine with machine learning methods to predict some output data, which are difficult to collect. In these works, 4 research gaps achieved in my thesis is to benefit winemakers, wine traders, and wine consumers. Phenolic compounds have a close relationship between product intrinsic cues and sensory attributes. So in my chapter 2, soft sensors are built to predict New Zealand Pinot Noir's sensory attributes for quality controls to benefit New Zealand winemakers. In chapter 3, soft sensors are built to predict New Zealand Pinot Noir's product intrinsic cues to maintain the reputation of authentic New Zealand wine traders. And in chapters 4, New Zealand and South Australian Pinot Noir's difference from phenolic compounds and sensory attributes are characterized by machine learning methods to increase the international market for New Zealand wine traders. And in chapter 5, machine learning methods are used to understand the relationship between New Zealand Pinot Noir's product intrinsic cues, sensory attributes, and phenolic compounds to benefit the nuanced consumers. Next, I will introduce how to select the New Zealand Pinot Noir wines. Firstly, all the Pinot Noir wines are purchased from New Zealand retail stores like Countdown, Paris website, Glengarry West, which are both available for the normal wine buyers. And to ensure the Pinot Noir wines diversities, so these Pinot Noir wines are selected from diverse regions, weightages, and price support. Firstly, I need to guarantee the New Zealand Pinot Noir wines from 5 regions, including the Central Otago, Marlborough, Nearestone, Martinborough, and North Canterbury. Among individual regions, it needs to guarantee the Pinot Noir wines have old weightage and new weightages. And among individual regions and weightages, I have to guarantee the Pinot Noir wines have a low price, middle price, and high price. However, sometimes it's very challenging to obtain the Pinot Noir wines with new weightages and the high price point. And due to the budget limitations, I selected the Pinot Noir wines with low price and middle price and high price with the ratio of 4:1. This is the softwares I have used in my thesis, which are both very common soft sensor, softwares like MATLAB, Python, SPSS, Pinot and Hyplot. In chapter 2, is balancing the cost and the prediction quality of soft sensors. Regression models and classification models are built to quantitative analysis and qualitative analysis. 35 New Zealand Pinot Noir has 35 sensory attributes to compose the sensory quality mapping. During build the regression models to quantitatively predict the New Zealand Pinot Noir's sensory attributes, PCA, the outliers are rejected by box plot, Auckland plot, and PCA score plot. And for how to select the significant explanatory variables by is use the PC loading plot, PRS, and the decision tree structures. And similar to the regression models, outliers in classification models are also rejected by box plot, top one plot, and the PC plot, score plot. But
Jingxian, can I ask you a question?
Okay.
I have a question. For the experiments, do you already have the results? You already have the results and you analyze them, or you are also involved in the experiments and you have to design the experiments?
I do my experiments. I design my experiments and do my experiments.
I see. And so when you say, like, for example, when doing tasting, who are these tasters? Are professional people or just random crowd?
You mean sensory attributes?
Yeah. So for example, you say eight mouthfeel. When you say here.
This sensory attributes is I purchased the total is 39 samples. And every sample includes 2 bottles. So totally there is 78 bottles. I like the New Zealand wine experts. They both have a WSTE certificate. They are professional wine testers. I let them to mark the scores. You can check and use the score from 1 to 10. 10 means the high intensities. It's similar to the Lincoln's University's experiments. They also do the same, but their sample is less. It's so, I let so the sensory data also is collected by myself.
No, I understand that, but the real data, like for example, 1, 2, 3, 4, 8 mouthfeel, that this data is from the professional wine tasters.
Yeah.
Okay, thanks.
Because I'm experiments is based, and the machine learning is for me is the tool. So this is the experiment that collected by my actual experiments. So for my and then because the classification models doesn't need to strictly the important data, so I select the important significant the explanatory variables are based on the label cost and the chemical expense. Here is examples about how to reject outliers by box plot, top-one plot, and the PCA score plot. And this is I let 7 panelists to do the sensory evaluation, so you can check. According to the official literature review, usually is the wine experts. You need to professional wine experts doesn't need too much. Usually is 6 to 20 will be enough. But if you like the novice consumers to evaluate some food and some like a beverage, at least the panelists need 100. All your results will be objective, no subjective. So this is the difference. So it's the samples about reject the outliers by box plot, top-one plot, and the PCA score plot. And here is the sample how to select significant explanatory variables by PCA loading plot, PRS, and the decision trees. In these chapters, soft sensors were developed to predict the new, and Pinot Noir is sensory attributes quantitatively and quality. The study offered a suggestion for select significant explanatory variables and for identify and reject outliers. And this study provides a range of budget and quality requirements for soft sensors for winemakers. In chapter 3, developing chemical soft sensors for predicting the product intrinsic cues of New Zealand Pinot Noir wines. Actually, I totally is like 39 samples, and every sample is to select contain the 3 bottles. So totally is 117 bottles, and their chemical data are totally measured by myself. So this 117 Pinot Noir bottles, 17 chemical parameters work as input data to predict the New Zealand Pinot Noir's regions, price point, and weightages. During building the soft sensors to predict New Zealand Pinot Noir's product intrinsic cues, there are some prediction errors. Here is the samples about the confused metrics of the soft sensors to predict regions of orange. And there are total 17 chemical parameters. And the relationship between the chemical parameters and the product intrinsic cues are evaluated by the future selection methods, include the random forest, extreme trees classifiers, gradient boosting classifiers, extremely gradient boost. And based on these figures, it can understand which chemical parameters have a close relationship with regions of orange. During I built the soft sensors, there have some predict errors. Two reasons at least to explain why there are some predict errors. Firstly, is some unimportant data work as input data. For example, I remove some unimportant data. The predict accuracy has increased. And the third reason is there have some chemical variances for output data. So, for example, 178 and 79 Pinot Noir they are from the same samples. It means they have the same regions, weightage, and price point. However, they still have a little bit of chemical variance, which can cause the chemical errors as well. In these chapters, soft sensors were built to predict the New Zealand Pinot Noir's product intrinsic cues to prevent illegal labelings, product against counterfeiting, and characterize the region protected designation of orange. Future selection methods were used to identify the key chemical parameters for determining New Zealand Pinot Noir's product intrinsic cues. Improper chemical parameters and chemical variance could lead to errors in predicting product intrinsic cues using soft sensors.
Jingxian, hi, Jingxian, I have a question. Can you go back to the plot where you compare all the methods? Previous one, this one.
This
here.
one?
No, the one that the next one. This one here. So I don't understand why, as you increase the number of inputs, the accuracy goes down. All the curves show that the accuracy goes down if you increase the number of inputs. So
no, George, it's
sorry. Okay, so it's the other way around. Okay, it's from right to left. Okay, 3 to 4. Okay, sorry, I got it. Okay, it's correct. Sorry, my bad. It's okay. You plot them from left to right, from right to left. Yeah. Okay.
Yeah. It's 70 numbers. Oh yeah.
But still in that plot, in the previous plot now, because we are doing something similar with other problems. So the XG boost seemed to be the most accurate, but against what? That's the accuracy here is against what? I don't understand. How do you define accuracy here?
I actually
is it against the is it against the professional taster, the soft sensor versus
no. This one is the chemical data, not it's my input data. This chapter is the chemical data is working as input data, and output data is like a product intrinsic cues, like you take regions of orange as examples. For example, I will let output the data is.
Oh, I see. This is just to tell you, this particular one is just to tell you about the region. But I was asking more subjective attributes, like mouthfeel, for example, that you have one.
Oh, these chapters don't involve the sensory attributes.
Yeah, okay. Okay, I got it. Okay.
Just the input data is chemical data, and output data is like central otago or marble multiples. So this chapter doesn't involve the sensory attributes.
Okay, I got it. Yeah.
And in chapter 4 is the comparative analysis of New Zealand and the South Australian Pinot Noir wines. Why select the South Australian Pinot Noir wines? From geography, locations, New Zealand and Australia are neighbor countries, and they are both famous for produce new world wines and competed with each other worldwide. And the South Australian Pinot Noir wines, actually 3 regions are predicted the New Zealand Pinot Noir wines in Australia, but the South Australian have a larger land, so because they are large land, so their price is more cheaper compared to Tasmania and like Southeast Australia. So in New Zealand, normal retail stores like Countdown is very general supermarket. They are very common and very cheap, just like $10 to $20. It's very common. So South Australian Pinot Noir wines offers affordable options to benefit wine buyers worldwide. And another reason is South Australian Pinot Noir are commonly found in New Zealand retail store like Countdown. It's the biggest supermarket in all New Zealand. These chapters involve the sensory attributes. It's total is 35 sensory attributes are selected by filter selection methods. And among 35 sensory attributes, 2 key sensory attributes are selected, which are used to characterize the New Zealand Pinot Noir and South Australian Pinot Noir. Based on the scatter plot, it can obviously say New Zealand Pinot Noir and South Australian Pinot Noir have different sensory attributes. And the 13 chemical parameters are selected by PCAs, and based on the results, it can check the total flavanols and the total anthocyanins can significantly characterize New Zealand Pinot Noir wines and South Australia Pinot Noir wines. Actually, during I do experiments, the South Australian Pinot Noir, if I use some acid to dilute it, the color is significantly different with New Zealand Pinot Noir. Their color is more rose red, and the New Zealand Pinot Noir, the color is looking like a more dark red. It's very obviously. And the Pinot Noir from vintage 20 and vintage 19th, New Zealand Pinot Noir have different chemical parameters with South Australian Pinot Noir. And Pinot Noir from nearest Martinborough and North Canterbury have a significant chemical parameters difference with South Australian Pinot Noir. With the help of canonical coefficient analysis, Pinot Noir aromatic profiles, mouth feeling, and quality indicators, together with chemical parameters, can significantly characterize the Pinot Noir from New Zealand or South Australian Pinot Noir. So in these chapters, South Australian Pinot Noir exhibit more intense sensory attributes, including tannins, granules, residue sugar, overall persistent and fresh vegetable aromas. Chemical parameters such as total anthocyanins and total flavonols could significantly different New Zealand and South Australian Pinot Noirs. Chemical parameters and sensory attributes could collaborate to distinguish between New Zealand and South Australian Pinot Noirs. And in chapter 5 is clarify the relationship between product intrinsic cues, sensory attributes, and chemical parameters. There are total 35 sensory attributes are evaluated by Y experts, and the classification tree structure are used to select key sensory attributes. And among the key sensory attributes, overall balance and fruit ripeness could cherry Pinot Noir from Central Otago, Marlborough, Nears, Martinborough, and North Canterbury. The region is, I checked the literature review, it should be the soil, because they have some metals in the soil, which can cause the difference from the sensory attributes. And among these 35 sensory attributes, they can include, they can divide it into 7 categories, sensory categories, like appearance data, aromatic profiles, basic taste, mouth feeling, flower attributes, quality indicators, and readiness for drinking. The high importance scores indicate the close relationship between the regions of origin. Take the how to calculate the importance scores of different sensory categories. Take the sample of the appearance data as example. The important scores of appearance data is calculated the average scores between the West Coast cities and the clarity. Based on this figure, it can infer that quality indicators have a close relationship between the regions of origin. So PCA are used to characterize the Pinot Noir from 5 regions, and the quality indicators, it can infer that North Canterbury and Martinborough have similar quality indicators, and Central Otago and Marlborough have similar quality indicators. Similar to the previous slide, the 35 sensory attributes are selected by classification tree structures. Clarity, fresh, floral aromas, overall persistent and okay influence could characterize the Pinot Noir with old vintage and new vintages. Similar to previous explanations, flower attributes and quality indicators could characterize the Pinot Noir from old vintage and the new vintages. So this is the results based on PCA results. So it can infer the majority of Pinot Noirs with old vintage are left in the positive with oaky influence, fruit redness, ridiculous notes, green notes, and the most of the Pinot Noirs with old vintage are positive with quality indicators. Similar to previously, clarity, secondary aromas, and overall persistent could characterize the Pinot Noirs from with different price point. However, the future selection methods are few to select the important sensory categories. And here is the PC results about the chemical parameters. It can infer that there is a certain relationship between Pinot Noir with old vintage and Pinot Noir with high and middle price. So in this chapter, so when consumers buy Pinot Noir from Martinborough and North Canterbury, or Pinot Noir from Central Otago and Marble, they may encounter similar sensory attributes. Consumer purchase older vintage of Pinot Noirs are more likely to enjoy high quality options. For winemakers, it can be inferred that selling Pinot Noirs would enhance their qualities. Additionally, extracting high total tannin levels and mature Pinot Noirs could improve both the sensory attributes and justify a high retail price. As for my future recommendation is expand the sample size of wines to select some New Zealand Pinot Noirs with price exceeding $18 and the vintage range before 2011 or to after 2020. Choose Australian Pinot Noirs from a variety of regions like South Australia, Southeast Australia, and Tasmania across diverse vintages and price point. Consider Pinot Noirs from other countries like French and the US. Consider experts from other countries. So this is my basic presentation.
Thank you so much.
I guess it's easy for yours because you are both do the machine learning methods.
Yeah, thank you so much for your presentation. Now we open the floor for our audience to ask questions. George, can you go first, or do you want to go first?
No, I was just going to say that the best Pinot Noir wines in the U.S. are in the Northwest, in Washington State and Oregon, actually. So that for your information, if you need to go there. But I was wondering if this data are recent or in the public domain. How did you find the data in the first place?
Huh?
The data that you analyze, where did you find them?
Oh, all the data is collected by myself. I buy the wines and do experiments, do sensory attributes.
But how did you recruit you didn't describe that part, so I'm a little ambivalent. How did you recruit the professional wine tasters and so on?
Oh, because New Zealand have a lot of Chinese to run vineyard. I find them. It's comparable easy for me to find some people involved in the wine industries.
Okay. Yeah, basically, the part that you didn't describe was the collection of data, which I think becomes important because the tools you use are pretty standard in classification, right? There's nothing. Also, for the outliers, by the way, for the outliers, you don't need to. You can use something called robust PCA. Robust PCA takes into account the outliers.
Yeah.
It's a different, but can you tell us a little more about the data collection? Because let's say I send somebody out to do a PhD on this topic for the wines here in America. How would they go about collecting the data? Just collecting the data for the attributes that you decided are important. Because you said you did everything yourself, but how did you? Did you develop a protocol for collecting the data?
Oh, collecting data. And the beginning, because I need to review because in the Lincoln University is Wendy. Wendy already do the one sensory evaluation is over 20 years. And I checked his methodology first. And they like wise to score get the scores from 1 to 10. So I check because if you do I know some people they do the scores like the 1 to 100. At that time is no meaning because sometimes professional wine testers like 98 and 97 they count to distinguish. So I think it's a score from 1 to 10 is very reasonable. And also literature review a lot of reference from like French and other countries. The majority people use 1 to 10 scores to mark the scores, like they test once and mark the scores. And then they select the methods for how to classifications is like in Lincoln's case is they have 18 buttons, like the French wine testers and the New Zealand wine testers to evaluate the 18 buttons. And they like the lowest, they can get the average scores, so from high to low, and they mark the lowest 9 buttons as the low price spot, and the mark the topest average scores 9 buttons as the highest scores. This is one method for classification models, and some is not use this method. Some is like the average the scores and the personality. Like if the average score is 1 to 3, they will official to let them to definite is the low price spot. If they are 4 to 6 or 4 to 7, they will set this score is middle. No, they don't consider the average. So sometimes maybe low price spot is larger numbers, or maybe high price spot is larger number. But the personally definition the price spot, like if average score is located in 1 to 3, they will let them belong to the low price. Average score is 4 to 7, they will let them to belong to the middle price spot. And if they are 7 to 10, they will be in high price spot. So this part is based on your personality definitions. Know the consistent definitions.
I see. So it's okay, yeah.
No one is fixed the definitions about the how to get the output data.
Right.
I think in a statistical analysis, it's very important that your sample data represent the population. So maybe I missed the part, but I cannot see any slides represent the number of male or female participated in data collection part. I mean the data from the males and females, or the age, something like the studied age of people, how you
Yeah, it goes back to the wine testers.
Oh yeah. Oh yeah. In my case is 6 is male and 1 is female. Yeah. But
because
it's already and the age is 23 to 40 year old. But I know some papers they write is 18s and but officially is reference is 6 to 20 will be enough, because I also be asked by the reviewers in the past. I literature allowed official for the wine professional wine test 6 to 20 will be enough.
Yeah, I'm very interested because I don't know, as long as you drink wine, you might be more expert. So if you study the, I don't know, the age of the sample data in their scoring or something like that, it would be very interesting.
To see if there are correlations. I think correlation with even the wine taster within the professional wine tasters, there's discrepancies. So you basically want to see if there are any correlations, hidden correlations in age, if the range of ages is big.
Oh yeah, I recommend your one software is from the Denmark, and this is the consumer check. Panel check and the consumer check is both free softwares, and in that softwares they can consider the consumers with different traits, like the age and the male and the females, they can, this software already developed. But one thing is, if you want to check consumer preference and consumer like, at least consumer need to over 100. All your results not accepted by reviewers. They will think your results is subjective. You can check consumer check and the panel check. And in YouTubers, they can teach you how to use. These two softwares is common in the, if some people to do the food preference and food sensory attributes.
Thank you. Are there any questions for the speaker?
Everybody's happy. I think everybody wants to have some wine.
Yeah. Okay, thank you so much. I think it's time to close the session.
Okay.
Thank you, Dr. Yishan, for I don't know I'm pronouncing your name correctly. Thank you for your talk.
Yeah.
So thank you everybody for joining us today. We hope you found this session informative and inspiring. We look forward to seeing you next week. Have a great weekend.